So, good morning, everybody. Welcome to the fourth webinar in the Resilex series. I'm Giulio Poggiaroni, the dissemination manager of the Resilex project, which is an Horizon Europe funded initiative that has the aim of reducing the EU dependence on external critical raw materials for battery and PV modules. This is the fourth webinar in our series. There are 3 more that you can retrieve on our website. And on our website, you can also find out some very interesting fact sheets that tell more about the technologies and achievements that we have developed in the project. And also a bunch of topical videos on the technologies and achievements that we did. So, enough from my side. Today, I'm joined by 3 distinguished speakers. Catherine Corriveau from 8 RawMaterials, the European Institute of Technology dealing with raw materials. Dr. Hamid Oubaha from the University of Liège-Greenmat Laboratory, and Dr. Willy Porcher from CEA in France. Few housekeeping rules. You can use the Q&A tab to post your questions, and use the chat for general communicate issues or anything. I will use the chat to share any relevant links. And I think we are ready to start. So I will give the floor to Catherine now. So Catherine serves as a business development manager for France at 8 RawMaterials, where she supports innovation and sustainability across the French ecosystem. She has an engineering background and a specialization in sustainability, and she previously spent more than 6 years delivering engineering projects and providing consulting services for heavy industry and mining sector. And today she will give a presentation focusing on the role of EIT raw materials in the battery sector across Europe. So, Catherine, the floor is yours.
Perfect. Thank you very much. I will drive you through the work that we're doing at EIT RawMaterials in the battery value chain. So, for those who are that do not know what is EIT in the EIT community, so EIT RawMaterials works under the umbrella of EIT, which is the European Institute of Innovation and Technology. And our role is to support the different actors that are part of the raw materials value chain and make sure to support them in different ways. So there's different clusters. So you have EIT RawMaterials, InnoEnergy, Digital, Climate Kick. There's several of them. So I represent EIT RawMaterials. And as part of our strategy or objective at EIT RawMaterials is to support the ecosystem from the exploration of raw materials and resource assessment to the mining in challenging environment, the increased resource efficiency in processes, substitution of critical and toxic materials, recycling and materials chain optimization, and the design and product of services for the circular economy. So as we can see, we touch on several different topics. And if we look at EIT RawMaterials and we have a look of all the different aspects or parts of actions that we have, so we have 4 pillars at EIT RawMaterials. So the first pillar is the funding opportunities. So we fund projects through the Horizon Europe program, and we have different funding mechanisms in place. We also have networking opportunities that we create for our members. The third part is the educational services. So we develop with universities lifelong learnings and modules to close the skill gap. And the last one is the innovation services through open innovation challenges and intelligence reports. So for the matter of this webinar, I wanted to focus maybe on the 2 first. So on the funding opportunities and the networking opportunities that we have at EIT RawMaterials in the battery value chain. So starting with the funding. So at EIT RawMaterials, we funded projects through upscaling projects. And we funded up to 83 million we provided up to 83 million in funding for battery upscaling projects in between 2023 and 2025, which represented half of the total upscaling projects that we did for this period. So when we say 83 million, it's both including both EIT raw materials funding and the co-funding by the partners. If you look on the map, you can see that those are like the different locations where we had battery-related projects in Europe that we funded. So as you can see, we had more projects in France, in Germany, and Belgium, and in Italy than other regions, but we still managed to cover many different regions and supported many different regions with those projects. Those projects, if we come back from the projects identified here on the graph and we go a bit more into a deeper dive into where those projects are located. If we look at the whole value chain, starting with exploration, mining, and processing, we can see that we have quite a lot of projects over there. We also funded and supported a lot of projects into the battery material space. Regardless if it's advanced materials, substitutions of materials, and everything that turns around that. We have, in general, a lot less projects in cell manufacturing than OEM, but still a lot of them that are part of the recycling part of the value chain. So those are the projects that were battery related that we funded. We also have other projects that we funded that are not directly related to battery materials, but a bit indirectly. So everything related to, for instance, the traceability of raw materials or the definition of the criticality of them, which are found in the column on the right in red. So then afterwards, by funding all of those projects, how it works with EIT is when we fund projects, the consortium also become a member during the duration of those projects. So through all those projects that we funded, we managed to have a very strong network of actors that are part of the battery value chain. So as you can see here, we have the whole value chain represented, or most of it. Again, mostly in the raw material sphere and recycling sphere, we are quite well represented. And then also into all of those who are focused on other services and technologies. So this is the latest information that we had in 2025. So maybe there's a few slight changes in 2026. So now we just finished covering the funding part of EIT, so how we fund projects, what kind of projects we fund. But then in addition of that, for our members, we also organize events to make sure that they connect in between of each other, them. So in the beginning of 2025, we decided that we would launch a new expert network for batteries. So we decided that to be able to break the boundaries in between the different countries in Europe and make sure that the actors would work across countries, we would create those value chain specific events. So we have one that is dedicated for batteries and started with the expert forum in April, where we gathered a lot of around 200 people from the whole value chain in a room for 2 days, where we had a combination of conferences, panels, and workshops as well. In addition, in September, and in line with the the Circular Economy Act that is upcoming in 2026, we decided to do a webinar on battery recycling. And for that, we brought to the table different actors from Hydrovolt, Celib, Stellantis, Umicore to bring different perspectives to the table. So those are internal events that we organized in 2025. But all those events allowed us also to create knowledge shared to our members that were part of those events. So that could access to the recap of the key takeaways from those events. Afterwards, in addition of the events that we organized, there's also events that we took place to make sure that we stay connected on the key trends and make sure that we connect with different actors from different regions. So we attended the battery event in both Dunkirk and Lyon, and my colleague Andrea, who is responsible for this battery network, also attended an event in October in Barcelona. And then afterwards, outside of what we do in Europe, We also got awarded the CRM facility by the European Commission. So the goal is we're working on it with InnoEnergy. And the goal is to connect European partners with international projects that could be of interest in order to do some kind of knowledge exchange and supply agreements. So the goal is not unidirectional. It's not only for Europe to benefit from this international community, but also for this international community to benefit from things that we might have in Europe related to, for instance, health and safety program, technology development, and things like that. So we also have this that is available at EIT. So we have different international missions that are organized by EIT and InnoEnergy on behalf of the European Commission over the year. So the countries that are identified in general and the business mission identified are often coming from the European Commission as a decision. So we're more on the operational side. And then finally, that's the overview that I wanted to give for this initiative that we have at EIT RawMaterials. So our senior advisor, Andrea, she's responsible for managing this ecosystem and also the different initiatives that will be taking place over the next year. So if ever you would be interested in learning more, taking part of it, there is a QR code here that will send you to the page of the science, which is the expert network that we're building. If you go down to this page, there is a form that you can fill, and then this can allow you to take part of maybe or get invited to upcoming events that we will organize over the year. So voila, thank you so much for this opportunity, and I wish you a good rest of the webinar.
Thank you, Catherine, for the very nice presentation. And I would like to remind our audience that if you have questions for Catherine, you can post them in the Q&A section, and we'll have a dedicated time slot at the end of the webinar to answer all your doubts and questions. So, time to move to the next speaker, which will be Dr. Hamid Oubaha from the University of Liège-Greenmat Laboratory. So, Dr. Oubaha is a R&D project manager at Liège, and he is specialized in the synthesis and recycling of energy storage material. His work focuses on sustainability and circular economy-driven solutions, including the upcycling of silicon recovered from end-of-life solar panels for use in lithium-ion battery anodes, which is what he's doing in the Resilex project that has a PV panel and battery focus. And today he will talk about exactly this, reviving end-of-life photovoltaic silicon for high-capacity lithium-ion batteries. So Hamid, the floor is yours.
Thank you, Giulio. Good morning, everyone. Thank you all for joining our webinars. So and special thanks to Giulio and Zaher for organizing this event. I see that many people are connected, which highlights the strong interest in this topic. Today, with my colleague Willy, we will discuss how we can valorize silicon recovered from end-of-life photovoltaic panels through the Resilex project results in lithium related to the lithium-ion batteries application. Before diving into the subject of our presentation, let me first give you a short overview of our laboratory for those who don't know Greenmat. Greenmat is a group of research at University of Liège. We are located in eastern Belgium, close to Germany. And our work is mainly focusing on synthesis and morphology shaping of inorganic materials for various applications, such as biomedical applications, 3D printing, energy storage materials. We have also significant activities in recent years in recycling, including recycling of end-of-life lithium-ion batteries and PV panels. At Greenmat, we are well equipped to work both at at lab scale or pilot scale, alongside with all the characterization techniques which allowed us to characterize and evaluate our materials. Our expertise in energy storage and recycling helped us to integrate consortia at both regional level or also at European level. Particularly Resilex project in which we are focusing today, which is Horizon Europe. We are also seeking collaborations for the the upcoming calls for this year or next year. So if you are interested in our expertise, we are happy to join in a consortium related to energy storage or recycling. So this brings us to the core of our presentation of today. So as you know, solar power is playing a key role in the energy transition to net zero. And if we look to the statistics, the solar power has contributed to the whole electricity production in EU by more than 9%, and this part is increasing sharply with the increase of the PV panels installation at residential or industrial fields. For instance, in Belgium, you can see that according to the PV cycle report published in 2024, we have more than 2 million new photovoltaic panels were declared. We see that there is a decrease compared to the 2023. This is related to the tax changes in Belgium and also to the saturation of the residential market. As may you know, PV panel has a lifespan of about 25 to 30 years, and the first installation can be dated to late 80s, early 90s, with rapid growth during the last 15 years. But this conducted to a large volume of PV panels that are now reaching end of life and are arriving to the recyclers. So the treatment of the PV panel waste, this new type of waste, and management is a crucial need. And this was anticipated at the European level through the Directive 2012-19 EU, which is pushing to recycle at least 80% of the retrieved panel. And now with our colleagues in Resilex Comet treatment, they are reaching more than 90%, sorry. The PV panels are designed to last in time under harsh conditions of sunny days or even winter days. So the composition is quite complex, including an aluminum frame. You have adhesives, you have glass, you have polymeric encapsulant, you have then you have silicon solar cells with screen printed connectors and wires, junction box. It's a complex mixture, so to be recycled is very challenging. And if you can see that even if silicon has constitute only 4% of the weight of the total weight of the panel, it contributes by half of the total module cost and embodied energy. And the market of PV panels are mainly dominated by the solar grade crystalline silicon. We can find between 600 gram to 1 kilogram of silicon per module. So the treatment of end-of-life PV panels is not just a recycling challenge, but it's also considered as a secondary source for critical and strategic materials. So this new type of waste is also considered as a urban mine where we can find valuable elements. In this context, a Resilex project develops a technological solution for reuse of silicon from different secondary sources, including mining waste, end-of-life PV panels, or silicon wafers cutting waste. By this, this project aims to reinforce the resilience and sustainability of the whole silicon value chain in Europe, and also to support the EU strategic autonomy. This Resilex consortium gathered more than 21 organizations from different countries across Europe. See that the Belgium is good represented in this consortium. And the structure of the project is quite complex. In addition to the work packages for the project management, communication, and life cycle assessment, this project is based on 5 technical work packages. 3 are focusing on recovery and purification of silicon, and 2 are dedicated to valorization by creating new application. In our case, we will focus on silicon carbon composite for lithium-ion batteries. Why silicon is interesting in the lithium-ion batteries application? Actually, the reaction between lithium and silicon is known since 70s. To form this reaction, form lithium silicon alloys. But if we look to this reaction, actually silicon reaction with the lithium can lead to a lithiated silicon which have 10 times capacity than used graphite. And this it takes actually 1 silicon to store 4 lithium ions, while in the case of graphite you need 6 carbon atoms to store just one lithium. Also, silicon has a relatively low working voltage, leading to high energy density. However, so there is always, however, with these advantages, there is many challenges related to silicon structure. Actually, this silicon is good at storing lithium. That its structure during lithiation expand to more than 300%. So this shrinking and swelling during cycling of the battery using silicon leads to the cracking and explosion, pulverization of the silicon particles, which conduct to an unstable particles and electrodes. So the key and the challenge is to find a way to stabilize this silicon structure. There is many strategies that are reported in the literature, and also some strategies are already in some startups, including innovation electrolytes, so playing with additives in the electrolytes, using also what the different binders, mainly some engineered polymers like conductive polymers or self-healing polymers. We have some people that are working in interface engineering by pre-lithiation, for example, or making artificial solid electrolyte interfaces. Also, some people are working in structural design by shaping the silicon particles in different way. In Greenmat and in the Resilex project, we decided at Greenmat to combine, to opt for a synergy between two technologies. With nanostructuring of the silicon and the silicon carbon composite formation. So to do so, we received from partners that are responsible of purification, of recovery and purification of the silicon. So we have clean and purified silicon fragments. These are the process of involved two steps of milling. So one dry milling, in which we can treat more than 2 kilograms per day. Then to prepare micro-sized silicon powder, and this micro-sized powder is then wet milled using organic solvent and using this semi-pilot continuous milling machine. And with this we can achieve more than 5 liters of suspension per day of nano-sized silicon particles. Then this silicon nanoparticles suspension is stabilized and optimized by some additives, including nanotubes or some polymers. And this stable suspension is now ready to be injected in the pilot machine, spray drying pilot machine, to produce silicon polymer carbon nanotubes secondary particles. And with this machine we can achieve more than 1.5 kilogram per week with a good yield of 82%. Then the obtained secondary particles are heat treated to obtain the final silicon carbon composite. And this now with Resilex support we are reaching 1 kilogram of this composite per batch. And to assess the stability of our process, so we produced different batches, and here I show the comparison between two batches. So you can see that the physicochemical properties of our silicon are quite similar, so attesting the good stability of our process. Then we evaluate this material in lithium-ion batteries at half cell configuration using commercially available electrolytes and commercial separator, and lithium metal as a counter electrode. You can see here that our composite, which is now called green CBAT, has good cycling stability, and up to more than 1,900 cycle, we still can deliver more than 900 milliampere hour per gram. So it comes to the conclusion. So with the support and the finding of European Union, we are now able to manufacture at pilot scale of our silicon carbon composite, reaching and taking a step further in TRL level, reaching 6 to 7. And our composite is now tested at CA with support with CCM. So now I will let my colleague Willy to continue and to explain you the achieved results on this context. Thank you very much for your listening.
Thank you very much, Hamid. And your presentation already ignited some questions that we will answer towards the end. Now
Yes.
we give the floor to Dr. Willy Porcher from CEA. He has a long-standing experience in working on silicon-based anodes, playing a major role in the development of the first battery featuring a full silicon anode produced in 2013. He has an extensive experience in silicon carbon composites, notably through the collaboration with Umicore that we saw mentioned in the presentation, and has authored more than 30 publications in the silicon-based anode field. So, Willy, the floor is yours. You're still muted. There you go.
Yeah. Thank you, Giulio, for this very kind introduction. It's maybe better like that.
Yeah.
So, yes, after Hamid's presentation on silicon carbon composite development, I will show you our contribution in Resilex project with demonstration of performance in a multi-layer pod cells of 2 ampere hour. So we assemble more than 20 cells. And so a 2 ampere hour cell is typically what you have in your smartphone. Here it's cells with 5 by 5 centimeter on 5 millimeter with 5 millimeter thickness. So it's small cells, but it's factor 1000 compared to coin cells presented by Hamid with previously. So I will start by
Sorry, Willy, I don't know if people are hearing you or not. I cannot hear you.
You cannot hear me?
No, I hear you. So
Okay.
Okay, sorry, Hamid, for you. So I will start by basic introduction on battery. It was slightly done already by Hamid, but to remind that in a battery we have a negative and a positive electrode. They exchange some lithium, and it's compensated the external circuit by a current. And so when you are in discharge, for example, we have a lithium going from the negative electrode to the positive electrode. And for safety reasons, we don't have lithium metal in a battery. And the lithium in intercalated or alloyed in active material. And in a conventional battery, it is graphite at the anode side, as said by Hamid, with low voltage, low potential, 100 millivolt around for graphite, and a capacity of 372 milliampere by gram. And so shifting to silicon, and we have a 10 times higher specific capacity. So it's a way to reduce finally the volume or the weight of this electrode and to improve the energy density. And the main challenge with silicon, it's really the expansion and shrinking of the material during lithiation, delithiation. And so with this material, you have like a bracing of your battery that you need to manage at every level, so at material level with the silicon carbon, but also at electrode level and at cell levels. And even if there is this expansion of factor 3, at the end, considering the lithiated material, we have a factor 3 on the of the energy density that we can benefit with the silicon. And so we expect at cell level, as the negative electrode is not all the cells, we expect an improvement of 20% of the energy density, or the energy density more or less the autonomy of your car or your phone. So going now to inside the cell, so we have these both electrodes, which are deposit on current collector, which is copper for the negative electrode and aluminum for the positive electrode, and separate by a separator to not have a short circuit, but only lithium exchange between both electrodes. On an electrode has typically a 50 to 100 micrometer active layer thickness with the shortest as possible current collector. And we depose on both sides the active layer. That means at the end 100 to 200 micrometer double side electrode. So in an electrode, we have also we want to maximize active material content, to minimize always inactive component in the cell. It's really key to achieve high energy density cells. So the active material is usually more than 95% of the electrode composition. And there is also a binder which has many functions. It's here to give adhesion to the electrode, its flexibility also. It will also contribute to process deposition, and also on the capacity retention, it will be a key component. And there is also some conductive additive as carbon black or carbon nanotubes. And they are introduced to really keep a connectivity between the particles to finally be able to collect the current up to the current collector. And there is also some liquid inside for the exchange of lithium to the other electrode. And so the idea is to really have the lower proportions. It's what we call the porosity before filling of the electrode, and the porosity should be less than 30%. So here is you have a picture of the coating machine that we use at CEA. So you have two coating machines in parallel. And so we will start from a slurry. It's a solvent on which we disperse all the electrode components. That means, for instance, the silicon carbon, the binder, and the conductive additive. And then we have here it's a coma bar system to deposit with very high precision this slurry on the foil. And really we expect high precision of less than 0.1 milligram by square centimeter. And so you have this first deposition, and in line you have the drying, and the solvent is removed. And at the end you can have electrodes. So here with this machine, we can have meters of electrode, like 10 meters of electrons, for instance. When you have a gigafactory, it's a kilometer by hour that you do. I would like to address the challenge that we had at CEA compared to the result presented by Hamid before in half cells. It was not this result. It was this result presented, but he demonstrates stab capacity for more than 1,000 cycles. I would like to come back to the parameter that we have in half cells. In the half cells, the capacity by square meter or the quantity by square meter are very low. It was here typically 0.3 milligram by square centimeter of silicon carbon, whereas we usually are more than 3 milligram by square centimeter in lithium-ion batteries. Also, in this result presented, there was only 1/3 of active material compared to 95% that we expect usually. There was no pressure applied on the electrode compared to the 30% porosity that we target usually. Mainly the main point is it's tested versus lithium metal, and so there is an infinite lithium quantity in this setup compared to lithium real lithium battery, on which we have limited lithium quantity. So when we assemble lithium-ion cell with high energy density, we have really a challenge to address, and particularly with silicon, with this swelling, we need to keep connected all the particles with a significant thickness of the layers. And so I show you here the first evaluation we did. So and compared to the electrode formulation that was used by Hamid, here we started by already 80% of silicon carbon composite, limiting the inactive components to less than 20%. We also increase the loading, and we densify the electrodes to have something more representative. So we start by the slurry dispersion, and already a good point. It was a really easy incorporation and easy dispersion of the material provided by University of Liège. You can see of these gauges, it's a micrometer slot, and we are able to detect the biggest particles, and there was no particles bigger than 20 micrometer. And even with less than 20% of inactive component, we were able to cut this disk that we will handle after to assemble these coin cells. And so the first coin cells results, so it's still versus lithium. We are versus lithium at 0 volts, and so you have this starting by the potentials. The alloying is in this plateau, and you have here the delithiation of the cells. So the specific capacity is by gram by active material, and you can see, yes, a very huge capacity of the composite provided by University of Liège. However, if we are able to put a lot of lithium inside the material, but only half of the lithium can be removed. It's not very nice to assemble energy density cells. To explain it, so with this electrode, we significantly reduce the anode thickness, but we need to compensate of this lithium loss. And we talk about initial Coulombic efficiency, which is the ratio of what you can remove compared to what you put in the material. If you need to compensate this loss, so you need a very thick cathode. So it was a key point to address at the beginning of this evaluation. What we did mainly with adding a single-wall carbon nanotube in the formulation. So really compared to carbon black, the single-wall carbon nanotube allow to keep the connection of particles. You don't have disconnection of particle, and so we are able to shift from 50% of initial Coulombic efficiency to more than 86%, which is quite nice value already. We investigate also lower silicon carbon composite diluting with graphite, so we have still something close to 80% of active material. Still a high reversible capacity compared to graphite with 360 million per gram. Here we are really much more specific capacity, and so with a nice initial Coulombic efficiency. So it was a first achievement of Resilex, this formulations development. However, regarding the next cycle, so it's the capacity are presented here, and you see it's really not a stable capacity. So it's versus lithium, and yes, the Coulombic efficiency that we the mean Coulombic efficiency on the following cycles was lower than 99%. And usually, to achieve 80% of initial capacity after 300 cycles, you need a Coulombic efficiency of 99.9%. So here we were really far from that. And we explain it by the interface between the material with the electrolyte, which is not stable. So anyway, we assemble some cells. So using the anode formulation with only 10% of silicon carbon composite. With these formulations, we achieve 850 ampere by liter, which is an improvement of 20% or 50% compared to graphite. So, and really, we really reduce the anoxicness with this formulation. So here you see after the different anode and cathode for 2 ampere cells using anode of 52 by 52 square millimeter and cathode of 50 by 50 square millimeter. We need a 17 anode and 16 cathode. That means for the more 20 cells that we assemble, more than 800 electrodes. So for that, we have a laser cutting process that we use to cut the electrodes, and also to scratch the tabs properly to be able after to collect the current. And so for cell assembly, we use a stacking machine. You have here the negative electrode, positive electrode, and so we have a Z folding process. The Z folding of the separator around the electrodes to avoid short circuits. And at the end, having some cells. So we assemble 24 cells, 22 without, I want to say, current leakage, 22 with a high quality. Thickness was 42 millimeter after assembly and 44 after the first cycles. 32 grams by cells, and really a capacity of 2.2 ampere hour with low deviation. You have here the voltage behavior of 5 cells, which is superimposed. Efficiency was 86.7% at the first cycles. So it's slightly lower compared to the half cell. It's due to extra surface that you need to put in the cells to avoid lithium metal, to avoid a safety issue. And at the end, we have a cell with an energy density of 250 watt-hour by kg, which is very, very high, especially if you consider the, I want to say, the basic foils and separator that we integrate. And so very, really high energy demonstration of the at cell level of this silicon carbon composite. Now on the capacity retention, and which was not solved previously at all cell levels, we keep when we have the full window, the full capacity cycle of the cells, we have a 1% capacity loss. I would say as expected from all cells measurements, shifting even to 2% of capacity loss after 15 cycles, and no more than 1 ampere hour after 40 cycles. So really low capacity. Even if we decrease the voltage window or the capacity use of the cells, we can improve to 0.5% the capacity loss per cycle, but really it's not good enough. When testing different voltage window at CSEM, so by Leonardo, we achieved to solve this capacity loss, to really stabilize the capacity, and demonstrating long cycling. We validated it at CS, so it's not exactly the main cycling, and we have some checkup every 20 cycles at CS. So, but really, yes, we can demonstrate long cycles with these cells having silicon carbon composites. So in conclusion, in Resilex regarding the activity at electrode and cell levels, we demonstrate that electrode formulation with single wall carbon nanotubes keep electrical conductivity during electrode bracing. We achieve initial Coulombic efficiency of more than 86%, compliant with high energy density cells. Thanks to graphite dilution, we improve again the initial Coulombic efficiency to something close to 88%. And so we achieve electrode with 850 ampere by liter at anode level, which is 50% more than conventional graphite anodes. And so 24 multi-layer pouch cells were assembled with 17 anode and 16 cathode, stacked by Z-folding process. So we add 1% of capacity deviation on the cell assembled, and we demonstrate energy density of 250 watt by kg with basic components. And finally, we demonstrate a long capacity retention by two partners by limiting the voltage window. Thank you for your attention.
Thank you very much, Willy, for this presentation dense of results. And actually, we have quite a lot of questions, so I will ask you and Hamid to be straight to the point. So I think I will start from you because one of the last questions was referring to one of the slides where you meant you used the word clean for the silicon fragment from the solar panels. They ask about which purity level.
Yeah, thank you for this interesting question. This is the purification of silicon fragment was done with the lixiviation, which means leaching of the metals, and what we achieve with this process in Resilex is what we call it's 99.9% purity, and for we noticed that for the in previous study at Greenmat that even metallurgical grade silicon works well for the lithium-ion battery storage.
Okay, thank you very much. There is a question addressed to Willy and Hamid about is it possible to process both batteries and PV panels within the same recycling line? If so, which process or facilities could be shared or mutualized between the two?
I can try to give an answer to this question if Willy has thing to add maybe later. Both processes, both sources of materials are different. So the dismantling of the PV panels are quite different than dismantling of lithium-ion battery cells. So you cannot use the same line to process the same both the materials, for sure. But for us in Greenmat, the process we used from what I presented today, combining the milling, the wet milling, and the spray drying, this could be used for both materials, but we work at material level. So when you have the black mass, for example, from the battery, or you have silicon, purified silicon from the panels. So this is, from this point, you can use our process for both, but you cannot start from the beginning.
Okay. I don't know if Willy wants to add something to this.
Well, maybe something very basic, but if you want to achieve a high level of recovery, of reuse, you need really specific process. And it's why for battery, for example, we developed the passport to really have after a specific recycling regarding the specificity of the battery. So I don't think that we can put everything in the same batch and have at the end a high quality of recycling. It's just a point of view of someone assembling some battery.
Okay, so staying on recycling, there's a question that contains many more questions, which is about the type of recycling technologies that are being developed in the project, but I think you already addressed this. And have these been validated at pilot scale, and what performance levels have been achieved?
This is a question from Idrisi, I think.
Yes.
The recycling technology developed in Resilex for this PV recycling involved the dismantling of the end-of-life PV panels. We have a partner that is treating that, is Comet Treatment, with the support of RICMA group in Belgium. So these two guys are processing tons of end-of-life PV panels, and the process that is developed to separate aluminium, glass, silicon, and also the purification are at pilot scale at Comet treatment, and the process is based on the shredding and grinding. Then you have a separation later on in the process.
Okay.
This is the perspective for the scaling up. It's already scaled up for the separation of glass and silicon, and but you have some problems with the polymer that is contained in to remove the polymer contained in these panels. And this is some people are working with the heat treatments or hot knives to separate the glass and also the polymer.
I see.
And what is recycling rate is currently obtained. According to our colleagues at Comet Treatment, they are achieving quite high yield in recycling of PVs. I think we can talk about 95%. But you have the problem of treating the glass, because the glass that is used in PV are not suitable for glass makers here in Europe. So because it contains antimony that is toxic, and they don't want to contaminate their lines.
Sure. Okay.
Is the consortium open to potential collaborations in this area?
Yeah, of
We are
course.
always open to collaboration.
Of course. I wanted to get back to Catherine, since this question touched upon the scaling up of industrial level and the validation at pilot scale. So, Catherine, not looking at Resilex, but looking at your experience at RawMaterials, about what you have seen, what you are seeing in Europe regarding the development of pilot scale sites and prospect for a scale up at industrial level. What's your take on this?
Yes, so like on our side at EIT RawMaterials, we have one funding mechanism that is available in place on a yearly basis to support those initiatives. So we have one that will be announced soon. So like they are currently working on the criteria, but typically what we fund at EIT's projects around TRL 5 that are looking to get to TRL 8 during a 1.5 to 2 years period. So those are the the projects we fund with a smaller consortium. So we go with up to 5 partners in those consortium usually. So for those that might be interested in learning more, there will be information that will be showed soon on the LinkedIn page of EIT RawMaterials, or otherwise, if you think that could be of interest for one of your projects, we can also get in touch. But in general, in the types of projects that we fund, it's like very, there are various. And what I would suggest is that if you have an idea of projects before starting working on an application, that usually takes time. We have people that are available to guide you and tell you if there's a chance or not, depending on like the
Mhm.
competitiveness and also if the project is aligned with our pillars. So we are there to support you before starting an application, to guide you in your application, make sure also that you put all the right things to be competitive. So I don't know if this answers your question.
Okay, okay. And perhaps what's your based on what you have seen, are there promising initiatives popping up in Europe?
There are many. The issue is for most of them we are under NDA, so we cannot necessarily
Okay.
speak about
Sure.
some projects that are developed with our industrial partners and research centers. But there are many projects related to batteries that are currently in development.
Okay,
Yeah.
so hopefully we will see a lot of noise in the coming years.
Exactly.
So I will take perhaps one or two more questions because we are approaching the limits of the webinar. There was one question about have you tested the recovered silicon material with LFP or NMC cathodes? If so, how do you address the very low first cycle Coulombic efficiency? Think both for Willy and Hamid.
Yes, we have tested our silicon with LFP and also NMC. Unfortunately, the first cycle is still we have a low initial Coulombic efficiency. We reached, if I remember well, 70%. But if you see during the presentation of Willy, he succeed with the CA formulation to go further and to reach more than 80%. So this is quite good. So it means that our silicon is working. You need just the optimization of the formulation, and also there is some other strategies to follow, but that we already tested, like pre-lithiation of silicon before assembling with in full cell. But we didn't disclose these results here yet.
Giulio, your microphone is mute.
Yeah, no, Willy, I want to ask you if you want to add something, or should I move to the next one?
No, we tested versus NMC in the cells. It's what I presented. We could have done it versus LFP. Maybe LFP is not high energy material, so it's not the good materials to evaluate silicon carbide anode. It's more dedicated to lower energy density, so more with pure graphite maybe.
Okay. One last question, then we come to the conclusion. So for LFP CAM production, what is the iron source used as a precursor?
Yeah, thank you, Mr. Emanjli. In this project, we didn't use we didn't prepare LFP. Actually, we used LFP, commercial available LFP.
Okay. Okay. I think it's time to come to the conclusion because we reached we went beyond 1 hour. I think we had a very nice overview on the activities we are doing in Resilex relative to battery, and also we had a nice overview on what EIT RawMaterials is doing. So I would like to thank our speakers, Catherine, Willy, and Hamid, for their invaluable contribution to this webinar. I would like to remind you that the recording of this webinar will be available on the Resilex website very soon, as well as the slides, and stay updated for the next webinars that will pop up. You can follow the LinkedIn page of the Resilex project to stay updated, and of course visit the website for checking the webinars, the videos, and the fact sheets. So thank you to all the attendees, and thank you to our amazing speakers today.
Thank you very much to all. Have a nice day.
Thank you.
Thank you. Bye-bye.
Bye.